Yesterday's Physics 2024, I think there was a question on moment. I'll send it to you. Okay, so that you have a taste of it and then report to me. So a spot is placed on the bottom of a slab made of transparent material of refractive index 1.5. The spot is viewed vertically from the top when it seems to be raised by 2 centimeters. This statement, a lot of you misconstrued it. When it seems to be raised. So once it seems to be raised, it means that dimension in question is the apparent height. Okay. Apparent height. Last time we looked at this concept and saw that if this is the slab, if this is the slab, and the spot is here, an observer viewing this from above will see this in this manner. A ray moving perpendicularly from the object goes undeviated. So when the ray is hitting in this manner, it will never be deviated. When the ray hits it at an angle, it will be deviated when it is moving out of the slab or the dense medium. So it will move away because it is coming from glass to air. So when you extend back the path of the refracted ray, then becomes the position of the object. So an observer looking at it from above, this is how he or she sees the object, which is an optical illusion. So from the surface to where the object lies, this is the real depth. From the surface to where the image, which looks like the object to the observer, this is apparent depth, RA. So we came to the conclusion that RD is equal to RA plus displacement. Okay, so the question given, we have the refractive index of the glass 1.5, and the object seemed to be positioned at 2 centimeters. And so RA is 2 centimeters. Therefore, we are to find then the height of the slab is, we are to find the real depth. So using refractive index equal to real depth divided by apparent depth. Apparent, okay, RA, or AB. Real depth will be equal to N times RA. N is 1.5, RA is 2 centimeter. Therefore, the height of the slab is 3. That's all. If you are to determine how the object is displaced, the displacement D will be equal to real depth minus apparent depth, and so 3 minus 2, and this will be 1 centimeter. So the glass slab, okay, bends the ray vertically by this amount, and that is the vertical displacement. That is the vertical displacement. All right. I hope it is understood. Class, I hope that part is understood. Okay, let's look at the question 2. The question 2, some of you were solving it as if it's a total internal reflection question. But no, it isn't. So, a ray of light falls on the glass plate of refractive index 1.5. What is the angle of incidence of the ray if the angle between the reflected and refracted rays is 90? A ray of light falls on a glass plate of refractive index. Excuse me. So we have glass plate. So let's use this as the boundary between so this is the glass plate. A ray of light incident falls on the glass plate of refractive index 1.5. What is the angle of incidence if the angle between the reflected and the refracted rays is 90? So as I told you last time, whenever a ray incident at the boundary, two things happen. Part of the incident light is reflected, part is also refracted. So once this is the normal, we have a reflected ray which obeys the law of reflection. That angle of incidence equals the angle of refraction. Then, because the ray is moving from air to glass, it will be bent towards the normal. Now we are told that the angle between the reflected and then the refracted is 90. So this angle must be 90 degrees. Okay. Our challenge here is to determine the angle of incidence. What is the angle of incidence? So if this is I, Of course, this will also be I, because under reflection of light, angle of incidence equals the angle of reflection. So yes, you can also represent this as R, but because we know that I is always equal to R, this can be changed to I. If that is I, okay, if that is I, what will be the angle of refraction? This is R. What is the angle of refraction? Okay, now we know that this whole angle must sum up to be 180. So if this is 90, Mommy, are you here? Eva and the rest of you. Leonard, I'm sure Leonard is not in yet. Let me check on attendance. So I have Batson, Cadmiel, Caleb, Della, Elizabeth, Eva, Ifwa, Joy, Julian, KJC, Calvin, Crispin, Leslie, Mamia, Marvino, Michelle, Millicent, Rashid, Safo, William, Yaira. That's all. Okay. Those of you who are here, thanks for joining. Enjoy your stay. So, if this whole angle is 180, and you are told this is 90, then it means that I plus R must also sum up to 90. So that when that is added to this, we have 180. Is that okay? Is that point understood? So if the angle between the reflected and then the refracted is 90, then these two remaining angles, angle of reflection, which is I, plus the angle of refraction, which is R, must also sum up to be 90. So that when we count this and this, which is 90 to 90, we have 180. Another way out is that, okay, R plus A plus 90 must be equal to 180. So that R plus I equals 180 minus 90. The value is the same. So whichever way you look at it, the value must be the same. If this is this, then R will be equal to 90 minus R. And we are making R the subject because we are going to apply Snell's law. Snell's law says that the absolute refractive index N would be equal to sine I over sine R. The reason for which we made R the subject here. And so we have the refractive index being equal to sine I minus R is now 90 minus R. So sine of 90 minus I. Okay. Now let's go into trigonometry a little bit. If I have a right angle triangle, interior angle of inclination, because this is 90, this part could also be 90 minus I. Because if this is 90, this plus this must also be 90. So if this is I, then you must subtract I from 90 to get this. Okay. A, B, C. Now let's take the sine of I, cosine of I. So sine of I is equal to A, B, C. From our diagram, Mommy, Michelle, from our diagram, what to be sine I? Michelle, from the diagram on the board, what to be sine I? Give me a response. Michelle, are you there? Okay, Elizabeth. From the diagram on the board, what to be sine I?
Please, A over C.
So sine, Elizabeth talking about sine of I. Sine
Sorry,
is
B over
opposite,
C.
exactly. So B over C. Then cos of I. Julian, what will be cos of I? Julian, please, when you are almost, do not waste time. Julian, Nana Sapo, Julian, hurry up, cos of I. Hey, Julian, are you there?
Yes, sir.
Okay, Elizabeth, what is cos of I?
Please, A over C.
So A over C. Let's also find sine of 90 minus I, the angle of depression. What is sine of 90 minus I? Gabriel, what is sine of 90 minus I? I get the step when you waste my time. Mamiya, what is sine of 90 minus I? It looks as if only Elizabeth wants to be talking today. Elizabeth, sine of 90 minus I.
Please, A over C.
Thank you. So A over C. And cosine of 90 minus I. Elizabeth.
Please, B over C.
Good. B over C. Look at what we have. You realize that can we equate one to the other? Looking at their values, which two terms can we equate? Quick one. Elizabeth, you are the only one who wants to talk. So hurry up. Which ones can we equate?
Sine 90 minus I is equal to cos I.
So sine 90 minus I is equal to cos of I and
Sine I is equal to cos 90 minus I.
Cos 90 minus I is equal to sine I. Okay, so because sine 90 minus I is equal to cos I, we can use that here. Sine I over sine 90 minus I as the angle of refraction. So we represent that with cos I. So this is the expression which will help us out. Now, from the same relation diagram, let's extract tan of I. Tan of I. What is tan I from the diagram? At least that we are hosting the show together, so don't forget.
Please, B over A.
B, good. B over A. Okay. Now let's take a ratio of whatever we have for sine I, whatever we have for cos I, and divide. So take a ratio of sine I and to cos I, and then give me the results. Class, that's what. Divide sine I by cos I, and then give me the results.
Please, B over A.
So the ratio sine I over cos I is equal to B over A, which is equal to tan I. You missed in solving this question. That is what most of you missed in solving this question. We've been able to extract that the absolute refractive index of the glass is equal to tan I. So the refractive index, you can easily find the angle of incidence at 1.5 is equal to tan of I. Therefore, I is equal to the tan inverse of 1.5. And what is the tan inverse of 1.5? What is the tan inverse of 1.5?
Please, 56.31.
Give it to me in 2dp.
Yes, please, 56.31.
3-1.
Yes, please.
That's the answer to the question. So if the angle of incidence is 56.31, let me add another question. What would be the angle of refraction? Yes, do it and then get back to me. You have to look for the angle of refraction. Everybody The light split. The light really split. Juliet, I'm waiting for your response. Something. Gabby. Yeah.
WZ.
Yes, I'm waiting for your answer. Doctor, what did you get? So you share your answer with us. I'm listening.
37.54.
So how did you know it? Just take us through how you got it.
Please, I divide the I over the N, the incident rate over the index.
But then, hold
Hold
on.
on.
I just want to take a shot of attendance. Give me some time to quickly do it. A lot of you are here and you don't want to come. Read that. And now we're done. Okay. All right. So back to the class. Number, you see, it is sine I and refractive index is equal to sine I over sine I. So if you just divide, it's a problem. It should be 1.5 is equal to sine I, which is 56.31 divided by sine of R. Okay, so making sine R the subject would help you find the refractive, the angle of refraction. Oh, okay, and then we've also established, one other way is that we also established that I plus R must be equal to 90. So if R is 56.3, then when we subtract that from 90, we must have R. Okay, so subtract 57 from this and then tell your answers with me. Just subtract 56.3 from 31 from 90. Mommy, I software and go. I'm waiting for you. Elizabeth, my co-host,
33.69.
33.69 degrees. Let's confirm using Snell's law. I just want to see, make sine R the subject, which is sine of 56.31 divided by 1.5. So whatever you get, when you finish, take the sine inverse and let's see what that would also give. Elizabeth, my co-host, read that. Amelia, Are we getting the same result?
Yes, please.
All right. So that's it. Please, any question on the solution so far? I think this basic trigonometry will help you out. It's very, very important in your mathematics and physics. So take note of it. And this is the reason why if you have a right angle triangle. Let me apply it to mathematics. If you have a right angle triangle and you are told this is 60, when you take 30 degrees, the other, if this is 60, the other angle will be 30. When you take the sine of 60 degrees, it must be equal to the cos of 30 degrees. And if you take the sine of 30, it must be equal to the cosine of 60 because of this relationship. Sine 60 is root 3 on 2. And cos 30 is also root 3 on 2. Sine 30 is half. Cos 60 is also half. It is because of this basic trigonometry. All right. Let's continue with total internal reflection. So we came to the realization that whenever light and tan of 30 degrees would also be equal to sine of 30 divided by cosine of 30 degrees. And tan of 60 would also be equal to sine of 60 divided by cosine of 60. Okay. So total internal reflection. So whenever light travels from a dense medium into a less dense medium, so one condition for total internal reflection to occur is that the light must travel from a dense medium, example, glass to air, water to air, glass to water. Of course, this is the normal, but it's based on the concept that whenever light hits a boundary, and the boundary is such that it is a transparent body, part of the incident light is reflected and part of the incident light is refracted. So this is I. When this is glass, part of the incident light will be reflected. The reflected ray obeys the law of reflection. Angle of incidence equals angle of reflection. Then glass to air, it will be deviated away from the normal. Deviated away from the normal. You realize that the reflected ray will be weaker in intensity or in brightness, and then the refracted ray will be stronger in intensity, meaning a greater part of the incident light is refracted. So this becomes the angle of refraction. This is angle of reflection, which is equal to I. Now, as we increase the angle of incidence in the dense medium, as we increase the angle of incidence in the dense medium, the angle of refraction will also be increasing. So we are increasing it. And so the refracted ray gets refracted to the normal. It also increases. Then there will be that particular angle of incidence in the dense medium, which would create an angle of refraction of 90. So when we have an angle of refraction of 90, then that particular angle is known as the critical angle. So that angle of incidence is termed as the critical angle. So we define the critical angle as the angle of incidence in the dense medium that creates or produces an angle of refraction of 90 in the less dense medium. And this is the requirement for total internal reflection to occur. When you manage to determine the critical angle of each material, so determining the critical angle of different materials total internal reflection can be achieved in the material. It's being said is that if you want total internal reflection to occur in a particular material or in different material, you must know their critical angle or angles. That angle of incidence, which will give us an angle of refraction of 90 degrees. Glass, for instance, has a critical angle of 42. Okay, so the critical angle of glass is equal to 42, approximately 42 degrees. What it means is that when you incident light in glass and you go to this angle, you will have the refracted ray lying on the boundary between the glass and air. Now, after attaining the critical angle, when you increase the angle a little bit, even when you increase the angle of incidence to 42.5, just 0.5 degree increase, you will have total internal reflection. The refracted ray adds to the reflected ray. So the moment you go beyond the critical angle of the material, this is what you have. Every light is reflected. So we wouldn't have a stronger refracted ray and a weaker reflected ray. The refracted ray adds to the reflected ray, and the reflected ray, which before was weaker, now becomes stronger or brighter, because every refracted ray has turned to reflected ray. This is what we call as total internal reflection. Okay, and the angle of incidence here is now equal to the angle of reflection. So the two main conditions for total internal reflection to occur is that light must travel from a dense medium to a less dense or rare medium. Then two, the angle of incidence in the dense medium must be equal to the critical angle. These are the two most important conditions for TIR or total internal reflection to occur. Please, if you have any question, ask. So, define or explain total internal reflection. Total internal reflection is the phenomenon whereby when light travels from a dense medium into a less dense medium, and the angle of incidence in the dense medium is greater than the critical angle of the material, the incident light is totally reflected within the dense medium. That's all. The phenomenon whereby when light travels from a dense medium into a less dense medium, and the angle of incidence is greater than the critical angle of the material, the incident light is totally or completely reflected. This phenomenon is what we term as total internal reflection. I can also expand that whenever light is, Maria,
Please, you said that the critical angle has to be greater than the incident angle of
the incident, the angle of incidence must be greater than the critical angle of the material. I must be equal or greater than C. When I is equal to C, you have the when I is equal to C, you have the refracted ray of the angle of refraction being equal to 90. And this is what is happening. If I is equal to C, this is what you have. But when I is greater than C, there wouldn't be a refracted ray. But if the refracted ray will add up to the reflected, and we only have incidence and reflection, total internal reflection.
I still don't understand.
Mommy, are we fast? Mommy, are listening.
How
You guys unmute yourself. Mommy, you don't understand how.
I don't understand how the eye is in what instant the eye is supposed to equal to the C. And when it's supposed to be
Listen to the explanation once more.
okay.
Starting from one medium, here dense medium to a less dense medium. Part of the incident light is reflected and part of it is refracted. So here, because the light is moving from glass to air, we have the refracted ray burning away from the normal. So this becomes the what? Mommy, at this angle becomes the what?
Angle of refraction.
So angle of refraction R. Okay. And so this is the refracted ray. This is the reflected ray. The refracted ray before is stronger in brightness or brighter, whereas the reflected ray is weaker in brightness or intensity. Now we want to gradually increase the angle of incidence in the SSI. We are progressively increasing the angle of incidence in the denser medium. Now we realize that as we increase the angle of incidence, will the angle of refraction increase or decrease? Maria? Maria, as we increase R, will I increase or decrease?
It will increase.
It will increase. Okay. Now, we are saying that as we increase I, there will be that particular angle of incidence where we have the angle of refraction to be 90 degrees, meaning the refracted ray will be on the boundary. This is 90. That angle of incidence, which gives us an angle of refraction of 90, is what we are calling as the critical angle. So, as I is equal to C, angle of refraction R must be equal to 90 degrees. At this point, we haven't achieved total internal reflection. The refracted ray is on the boundary. The reflected ray is here and is also equal to C. There, the refracted ray is brighter or stronger in intensity, whereas the reflected is weaker. All that is happening is that the angle of incidence is equal to the critical angle of the material. So I said different materials have different critical angles. The critical angle of glass is 42 degrees, meaning that when you incident light in glass and the angle of incidence is equal to this, you have the angle of refraction being equal to 90. Are you okay? Are you okay?
Yes, please. Yes, please.
Good. So, then in a material, you must know the critical angle of the material. Where the incident ray must be at what angle? Okay. Now the movement is greater than 42 or C. If the angle of incidence is greater than the critical angle of the material, now this is what will happen. Every refracted ray acts to the reflected. So, okay, please give me a second. Okay. So when is greater than C, every reflected pass to the every refracted ray pass to the reflected. And so this time around, we only have incident and then reflected. Okay, the reflected ray, which before was weaker, is now stronger because the refracted ray has added to it. And this is what we are calling as total internal reflection. Now, yeah, is that okay?
Yes, please.
So it means that for total internal reflection to occur, the angle of incidence must be greater than the critical angle of the material. If I is equal to C, you have the angle of refraction being 90. That is not TIR. But when I is greater than, then every incident ray is completely or totally reflected. That's the whole history. What are the applications of this? Okay, let me talk about the mathematical application here before we look at the real world application of total internal reflection. Now, what about lights? This is glass. Let's assume the refractive index of glass is mu J. The refractive index of another medium, which is, I would call it air, but mu G must be greater than mu of, instead of glass, you let me make it 1 and 2. So the refractive index of material 1 must be greater than the refractive index of material 2, and total internal reflection would occur. The reason for which the first condition says that light must travel from a dense medium to a less dense medium. So instead of glass and water 1 and 2, we earlier learned that the product of the refractive index of the first medium, mu1, and the sine of the angle of incidence. Here, the prerequisite or the requirement is that you must know the critical angle. Okay, so if I know the critical angle, then I can increase it a little bit to have total internal reflection. So this denser material, its critical angle is not known. Okay, you are the physicist or the engineer. How will you calculate it? So C is the critical angle. That's the product of the refractive index of the first one and the sine of the angle of incidence, which is sine C, must be equal to. Oh, which answer? Mute yourself. Must be equal to the refractive index of the second medium, mu2, times the angle of sine of the angle of refraction. If C is the critical angle, then the angle of refraction will be 90. So mu1 times sine C must be equal to mu2 times sine 90. Mu1 sine C is therefore equal to mu2. God sine 90 is 1. mu1 will have sine C is equal to mu2 over mu1. C therefore is equal to the sine inverse of mu2 over mu1. What does this relation mean? So if I want to determine the critical angle of a particular dense material, the equation tells us that just divide the refractive index of the less dense medium by the refractive index of the denser medium and take the sine inverse of this value, and you have the critical angle of the material. That is the meaning of this. Now, if it happens that the low dense medium is air, so this applies to when you have one dense, one less dense, but the less dense medium is not air. If the lower dense medium is air, if rare medium or less dense medium is air, the refractive index of air and vacuum is 1. The refractive index of air and vacuum is 1. So if the less dense medium, mu2, is air, this is how the expression will look like. Sine C is equal to 1 over mu, the absolute refractive index of the denser medium. This is also stated in books as 1 over mu. Don't forget the symbol representation for refractive index can be this or this. So if the left dense medium is air, all that the theory is saying is that to find the critical angle of the material, just take the sine inverse of 1 on the absolute refractive index of the dense medium. That's all. So look at something. We know the refractive index of glass. The refractive index of glass will be 1.5. Then the refractive index of water is 1.33. We can easily use this information to calculate for the critical angle of glass and water. Do that for me now. Help me use these two information to find the critical angle of glass and water respectively. Are we done? Mommy, are you done? Mommy, I have gone. Elizabeth, my co-host.
Yes, please.
I'm hosting this show today with you. The rest are not willing to talk.
Please, 41.81.
So it's a 41.81, meaning it's approximately the 42 degree IA. Okay, what it means is that if you want TIR, total internal reflection, to occur in glass, just incident the ray at 42. Okay, and you have the refracted ray being equal to 90. Then when you go beyond 42 degrees, you have total internal reflection. What did you make for the critical angle of water?
48.75.
48, approximately
0.75.
so 49.
Yes.
Meaning if you have water air, okay, interface, and you want light to be totally reflected within water, direct the angle of incidence at an angle a little bit greater than this, and you have total internal reflection occurring. So knowing the critical angle, you can easily obtain total internal reflection. And so the prerequisites of TIR is knowing the critical angle of the material. So these are the relations that will help you determine the critical angle. But this one goes to when the rare medium or the less dense medium is not air. And this one is for when the less dense medium is air. So please take note of the two and apply them accordingly. Any question? Any question? No question. Au
Mr. Dear,
Hello.
please, I wanted to ask that under which condition will I be equal to C? Like he said, at first he said when I is equal to C, total internal reflection will occur. And now he said it's rather when I is greater than C. So I want to ask that then under which condition will we use the I is equal to C one?
All that I said is this. If I is equal to C, okay, that is the requirement for having or obtaining total internal reflection. When I is equal to C, This is what will happen. The angle of incidence in the dense medium, then the angle of incidence is equal to the critical angle. And this is this. If we have this, you wouldn't have total internal reflection, but you have a situation where the angle of refraction is 90. This is not total internal reflection, because with this we have reflected ray, we also have refracted ray. The only thing is that the refracted ray lies on the boundary between the two media, plus air, for example. This is not total internal reflection. But what I'm saying is that I know this. When I know the angle of the lexical angle, I can easily figure out how to cross total internal reflection. Because all that it means is that for total internal reflection to occur, the angle of incidence must be a little bit greater than C. But if I don't know the value of C, I cannot, it will be difficult for me to have total internal reflection. So for TIR to occur, the angle of incidence must be greater than the critical angle of the material. But this will help us, okay, to get there. I is equal to C will easily help us to get there. Have I explained?
Yes, please, I understand.
So that's how it is. Please, if something bothers you, ask questions. Okay, feel free by sending a text or mastering the courage to ask, as your colleagues are doing. All right. Applications. Applications of TIR. TIR is super important. It is used in communication. Telcos, MTN, Vodafone, now Telecel, Airtel, Tigo, Nathan. It is applied in communication and in the health sector. What is it used in communication? Total internal reflection is used to transmit data and voice signals of higher efficiency compared to transmitting voice and data signals on copper wires. The copper wires, telephony, household telephony, internet, and all that. You see, just recently, I don't know if you got the news that MTN data cable in the sea was disrupted by, I think, a ship or something like that. I don't know if you heard that news or you were in school then. Hello, class. Did you receive that news or you were then in school?
Service we were at home.
Okay. You see, that's unfortunate accident. Yes. Okay. Happened because the telcos, MTN's fiber cable was damaged. Okay. And the fiber cable is routed through the sea. And this is fine or very small glass tube. It's like wire. But this glass tube is used in place of the wire, copper wire. for channeling information from one point. So in this like this, now instead of sending information through the cable, no, they use what we call fiber glass, also known as cable. The cable uses the principle of total internal reflection. All that they do is that because they have an idea of the critical angle of mass, light, information transmitted in the form of is transmitted in the form of light. Now, in using wires, information is transmitted in the form of electrical, currents or electricity. Now, the information being sent is put in the form of light, and it is incidented at the critical angle. So they know the critical angle of that. So once you have an idea of the critical angle of glass, because total internal reflection, what you need to do is that the angle of incidence must be greater than the critical angle of the material, and the light is transmitted with greater speed, total internal reflection, on and on and on at a greater speed. The advantage of this over the copper wires is that one, information can be transmitted in more very large voice and data can be sent through the fiber cable of optical fiber. It is transmitted at layers. It is travels at the speed of light, 300 meters within a second. So the speed of transmission is very, very high compared to transmitting on cables. So both messaging or data and voices, and it is transmitted at a high speed. The other advantage is that, you see, I don't know if you've observed that before. Sometimes when you are speaking on telephone, not the mobile phone. Sometimes you will be there and you hear somebody talking at the background. You'll be talking to somebody, all right, but within the phone, somebody else can be talking as well. That is crosstalk. Talking and somebody crossing to talk on your line. Crosstalk. Crosstalk usually happens when two or more wires combine or touch. Okay, but in fiber cable, crosstalk is eliminated. The only problem is when the cable is damaged, like it happened in the sea. Okay, when it's damaged, then the glass is broken. It must be replaced or repaired. So it is applied in communication and in health sector. In the health sector, the principle of total internal reflection is used to diagnose inaccessible body parts. Example, endoscopy. I've gone through endoscopy before, where I felt like something within my throat. And if medical practitioners or doctors must examine my throat, there is no way they can just cut and then no. And so what was done was actually passing light through my throat. The light incidented in the throat is viewed on a monitor. So when the light is pushed through the throat, whatever is in there will be shown on the monitor, endoscopy. So it is used to assess or check inaccessible parts of the human body. Okay, maybe you want to then something is pushed in there to display the information on a monitor. So fiber cable is also used in that regard. Please, any question? So this is one application of the fiber cable used in communication and then used in how to diagnose inaccessible parts of the human body. The principle of total internal reflection is also applied in mirage formation. Mirage formation. It is also applied in prism periscopes. We have mirror periscope and prism. Mirror periscopes are using mirrors, but prism periscope are also be using glass prisms. The total internal reflection is also applied in binoculars, but the binocular views. So that's gadgets, which is used to view object at non-telescopes. Binoculars are used to view object at a closer distance. Okay, whereas for telescopes are for close range. Binoculars are for close range, whereas telescopes are, tele means distance, scope means view, so distance view. Okay, so these are some applications of total internal reflection. We have a lot of them, but I think I've given you four, and it is enough. All right. Formation of application is the fish of total internal reflection is the fish eye view. The fish eye view. I've given you 5. The fish eye view. The fish is such that it can have 360-degree view in water. Fishes, okay, in the water do not need to turn to see close or different angle viewing. By total internal reflection, fishes are able to have about 180, I mean within the water medium. And then above, yeah, they also have 180 view up, but that is not by total internal reflection. Within the water, they have about 180 view of their environment. All right. Mirage formation. Mirage formation. We need to talk about mirage formation. How is it formed? A mirage is an optical illusion due to refraction of light. So last we spoke about how it is created. During sunny days, when you're having to take a walk, either in a car or strolling on the road, you always see a mirage, the apparent pool of water on the surface of the road. This pool of water, you chase as you walk towards it, it also moves away from you. So there is a saying that you can never catch a mirage. This is a philosophical saying by Mr. Ibia. You can never catch a mirage. Those people who take walk on the desert, okay, also have their say on how mirage deceives them on the desert. You know, on the desert test, because of the harsh weather condition, okay, the chances of them becoming thirsty very high. So as they walk and then look ahead, there always appears to be a pool of water ahead of them. Okay, being thirsty and then seeing water, naturally you would rush to think to quench your thirst. Only for them to realize that as they rush to it, the pool of water also, goes far, far away from them. Okay, so they also have their say or view on how mirage describes them. How is it for? This is the surface of the road. This is the sun. And color between the road and then the sun. Now, when the sun shines, in fact, the closest air layer to the surface of the road becomes so heated than the layers above. This is because the road surface, there are gravels, okay, the bitumen with different heat capacities, and sand, gravel, stones have lesser heat capacity, meaning that they can, when they absorb thermal energy, they can easily be heated up, can air than liquid and all that. Solids generally, okay, have very low capacity. They are easily heated. So if these are gravels and stones and they are easily heated, when they take the heat energy from the sun, they can easily be heated. It means that the layer of air above it, because these are hot materials at that higher temperature, the air layer above it will be hotter than the air layer here, here, here. So this first air layer has a higher temperature than this one, 3, 4. So let me label this as T1, T2, T3, T4. And this is the reason why it is said that the higher you go, the cooler it becomes. Air, for instance, it's more like an insulator, thermal insulator. The heat energy with the diesel is radiated, or yes, radiation is reflection of thermal energy. So as we go up, as we move, temperature decreases. So decreasing temperature of the air as we go up. Okay. What it means is that the sun and the ray coming from the sun here passes through layers, air layers of different temperature. Now, when the temperature increases, air becomes less dense. So when you are in a room and the room feels warm, the first remedy is that open the windows, okay, so that warm air is less dense. The density of warm air is less. So it can easily be displaced by cool air from outside. So the room feels warm. You open the window so that cool air can blow from outside and come and displace or push away the lighter warm air out of the room. And this is what is termed as convectional air current. Because the temperature of the road is high, the air layer here has a lesser density than the air layer here, than this one. So in terms of density, this is less row 1, row 2, row 3, row 4. Because the temperature of the first layer 1 is high, its density is lower than this. So this is lower, higher, higher, higher as we go up. So the light coming from the sun passes through every layer of greater densities. If it is coming through every layer of greater densities, it means of greater refractive indices, because density goes with refractive index. If a material is dense, it means its refractive index is higher or greater. So the light ray or rays coming from the sun passes through a layer of greater density. So let's pick this first layer. Light coming from the sun, because it is from higher or denser air layer compared to this, how will it behave or how will it deviate? It will deviate away from the normal. When it gets to this one, this will also deviate away from the normal. When it gets to this one, it will deviate away from the normal. When it gets to the ground, it will further deviate away and then reflect. So it is deviating away because the light is traveling from denser medium to a less dense medium, denser medium to a less dense medium, denser medium to a less dense medium. So it is being diffracted away. By the time it hits the road, it will just reflect in this manner, and an observer coming from afar, either you walking on the road or being in a car, will see the image of the sun as if it's a pool of water on the surface. And that is what you will see as a mirage. Okay, so to successive refraction of light, the light ray from the sun passing through every layer of greater density to a less dense air layer, on and on and on. That's successive refraction. The light ray is refracted, and so it appears to an observer as if the sun is a pool of water. So that the pool of water is what we see as a mirage. This is what creates a mirage. This is what forms or creates a mirage. Please, any question? Can we move on?
Mr. Elia, please. I wanted to ask that, is it the image of the sky that appears or the image of the sun that appears?
It can be. The thing is that the rays, the sun, the temperature of the environment is becoming hotter, and due to the rays from the sun. So it is the rays from the sun that we see. The image of the sun, which is refracted, that we see. Sometimes at a distance, you can also see the image of the trees around. So mirage can be the image, the virtual formation of the image of the sun and the trees around.
Okay, thank you.
Julian.
Yeah, so is it different from seeing your reflection in the water or something?
That's different. Seeing your image okay, in water is due to regular reflection. I don't forget I said that regular reflection occurs on surface of calm water and smooth surfaces. Okay, so because the surface is smooth, you can see your image. And I also said that regular reflection causes formation of virtual images. So that is different from mirage. And for mirage, it only occurs during hot, sunny afternoons. Regular reflection occurs so long as the surface is smooth and the surface of the water is calm. Is that okay?
Yes, please.
Then let's switch to refraction of light in rectangular prism. Refraction of light in rectangular prism. A rectangular prism is a glass block which is shaped in a rectangular form. When you go to school, you see that in your laboratory. It's just a glass block shaped in a rectangular form. We also have triangular. Those ones that are shaped in a triangular form or shape. This is the width of the glass block. So it's just similar to the phone. Okay, but just the phone shaped in a rectangular form, but it's a glass block. So this becomes the width of the glass block, the width. So the width is represented as h. Please give me a minute to check. So h is the width of the glass prism. The glass block in the lab is actually used to determine the refractive index of a material. And it is also used to investigate this concept of when light travels from air to glass, it is deviated towards the normal. When light travels from the glass to air, it is deviated away from the normal and all that. So we use this to also test these theories. And we can also use that to find the refractive index of the material glass. So we draw a normal. So usually in the lab, you trace the outline of the glass prism. Then you draw a normal. A normal is a virtual line or a line which is always perpendicular to the boundary or the horizontal boundary. Okay, let's label the point A, B, C, D. So this is the normal. So in the lab, you'll be given different angles. Maybe I, starting from 30, 40 in that increasing or decreasing manner. So you measure the first angle, and that becomes the angle of incidence. The incidence ray, you push 2 pins, 2 pins, P1, P2, space 5 centimeter, 5 centimeter interval between them. Then what you do is that you look through the other interface, BC, okay, to trace the image, and you are going to put 2 other pins here so that those 2 pins placed at this side will be in a straight line with the 2 you see here. Okay, so you look through the glass prism and then push 2 pins so that they will be in a straight line with the 2 pins P1 and P2. Practically, that is what you'll be doing in the lab. Now, after pushing maybe P1, P3, and P4, and this is what appears to be in a straight line with these 2. Then you join these 2 pins to the boundary DC. So I join these are rays emerging out of the prism, and so we call this as emergent ray. This is the incident ray, then emergent ray. Then you indicate this point, draw a normal. The normal must always be perpendicular to the horizontal boundary. Then what you do is that you join this point to this point. This is a refracted ray. So incident, refracted, emergent ray. Please, ray diagrams must be shown with arrows. Okay. So this gives us the angle of refraction, R. The angle between, this is normal 1 and then normal 2. The angle between the emergent ray and the normal is equal to the angle of emergence E. So I equals angle of incidence equals angle of refraction. And E is angle of emergence. All right. Ideally, you see the incident ray, the part of the incident ray is supposed to be straight, but due to the fact that light travels from air to glass, the path is deviated. So when you extend the original path, this angle, what name do we give to this angle? Class, what name do we give to this angle?
Angle of deviation.
Angle of deviation. So this is sigma. So practically, you'll be doing it for all angles because you have to measure I, deviation, and E. So from what we've done, we can deduce that angle of incidence I by vertically opposite reason is equal to angle of refraction plus the angle of deviation. So sigma is equal to I minus R. And this is something we've actually learned earlier. Okay. Now we see that the ray is supposed to go straight, but it's been deviated to the extent of deviation by this angle. A perpendicular line drawn from the second normal to this line gives us the lateral displacement. So when we draw a perpendicular line to this, you have the lateral displacement D. So how the displacement is a distance. The distance through which the original path has been deviated. The lateral displacement. So D, small letter d, is known as the lateral displacement. Lateral because it is displaced horizontally. Okay, so let's look at the theory we can derive out of this. Then you want D. Questions can be such that calculate for D and then determine the refractive index and so on and so forth. So Snell's law is equal to sine of I, angle of incidence, divided by sine of R, angle of refraction. That is 1. Now, this is a normal, so this line is also perpendicular to this. So let's label whatever we have within. We have O, we have A, B, C, D. So O, E, F, J, yes. So look at what we have here. We have 2 rectangle triangles over here. We are talking about triangle OJ and triangle OEF. Okay. Our main aim is to find B. Okay. Now we consider triangle OLB. This side, the adjacent of the triangle is H, the width of the prism. So this can always be measured. Even if you don't know and you pick a rectangular prism, you can always measure H. So when we take the cosine of angle of refraction cos R is equal to the adjacent, which is H, over the hypotenuse OF. Then when we take sine of the angle of deviation, sine sigma, this is equal to D opposite D over the hypotenuse OF. Sine sigma is equal to D over OF. OF is common. So let's make the subject in this and then in this, and then we do it. Okay. These two right-handed triangles share the same hypotenuse. So AF in this is equal to H over cos of R. OF here is equal to D over sine of the angle of deviation. So when you equate this, we have H on cos R is equal to D on sine sigma. From this, then the displacement D is equal to H times sine of the angle of deviation divided by the cosine of the angle of refraction. So this is an expression which would enable us to calculate for the angle of the horizontal or lateral displacement molecular D. This relation can be expanded as D is equal to H sine of course, angle of deviation sigma from the top. This is how we calculated it. So we can expand this relation as sine I minus R divided by cos of R. What it means is that we can use equation, the Snell's law, to find the angle of refraction, knowing the refractive index. Then use I value here to calculate for the lateral displacement small d. Okay, so this is the theory on refraction in triangular prism. Refraction in rectangular prism. This is a theory we'll be using for refraction of light in rectangular prism. So, is any question? Now, maybe I do any question.
Yeah, please.
Oh, okay. Okay. All right. The next thing that must be treated will be lenses, and then we look at refraction of light in triangular prism. Lenses, we can go through lenses so quickly because the whole concept is similar to mirrors. Okay, concave and then convex mirror. So I think we can sail through lenses. But our last meeting is on Friday. So on Friday, we need to go through this with some speed so that we can touch on. My earpiece is gone. We need to go through this so quickly so that we can touch on lenses and refraction of light in triangular prism. Okay, so it's going to be fireworks. And on Monday, on Friday, I think we'll have to be doing our last evaluation. Yes, it has come to stay. So you would evaluate me for the last. And so we really need to manage our time very well. Okay. All right. I think we'll end here. As usual, your assignments will be sent. This time around, the last one I sent, only a few of you made time to do it. Okay, very unfortunate. So this is where we draw the curtain on today's meeting. Thanks for your time. Thanks for your silence and everything. We'll have another wonderful session on Friday. Until then, may the good Lord be with you and nice day. Bye-bye.
All right, sir.
Crispin, the next class, I think, is Friday. Our last meeting will be on Friday. Okay. Bye-bye.